This is session D2 on two-state systems. Last lecture D1 was on spin in the Stern-Gerlach experiment from 1922, in which intrinsic spin angular momentum was discovered in an experiment involving magnets and neutral silver atoms. The atoms split into two beams, and so that is a two-state system, and today we will explore two-state systems. Two-state systems are the simplest possible non-trivial quantum systems. These are idealizations when other degrees of freedom of the system can be ignored. The electron has a two-state system with respect to its intrinsic spin angular momentum when we're able to ignore its position and momentum spatial state as being independent from its spin. Courses and books generally probably teach spin 1/2 first and two-state systems second, leveraging spin 1/2. I will reverse this and teach two-state systems first and spin 1/2 second, leveraging two-state systems. I choose this approach because much of what we learn as special with spin 1/2 is actually a consequence of two-state systems. And when we study spin 1/2, I want to make it clear what is unique to spin 1/2. So we'll do two-state systems first. I used the previous lecture D1 on the Stern-Gerlach experiment to show that there is a physical system that is a two-state quantum mechanical system. The term two-state system is a little misleading initially. Each such system has an infinite number of states, not two, but they can be expressed as a linear combination of our choice of a pair of independent, non-overlapping physical basis states. So there are two orthogonal physical basis states selected for the particular physics of that system. So a two-state system has two orthogonal basis states. The choice of basis states is not unique, though often there are obviously useful choices. An individual spin 1/2 particle, such as a single electron, has spin states that are two-state systems, independent of the electron spatial state. However, there are also other systems that can be described by two-state systems, which is why we're separating two-state systems from our learning about spin 1/2 particles, which we will continue in the next lecture, D3. So, some two-state systems. A single spin 1/2 particle, such as an electron, proton, or neutron. For example, nuclear magnetic resonance, NMR, and magnetic resonance imaging, MRI. The interaction of the spin of the hydrogen atom's proton with a time-dependent external magnetic field. That is a two-state system. Photon polarization. Even though photons as particles are spin 1 particles, but they have zero rest mass, they're traveling at the speed of light, and their polarization is a two-state system. Lasers and masers, excited state and ground state, and transitions between pairs of electronic states generally. Electronic states are more complicated than two states, but we can usefully focus on two states and get information about those two states and transitions between them. For the ammonia molecule, NH3, nitrogen and 3 hydrogens, the ground state and first excited state spatial wave functions, not for the electron, electrons, but for the location of the nitrogen atom relative to the plane of the 3 hydrogen atoms, where the nitrogen atom can tunnel through the potential barrier. That and the effect of an external electric field can be described as a two-state system. This is the basis of the ammonia maser, which predated the first laser by at least 10 years. And atomic clocks, the physical systems inside atomic clocks, can be viewed as two-state systems. Once we learn about and understand spin 1/2 systems, any of these two-state systems can be imagined as analogous to a spin 1/2 system if you take the proper care, but our approach will be to learn two-state systems first. This is a possible time to take a break. State space and basis vectors. The state of a physical system in quantum mechanics is mathematically a vector in a complex vector space. The state space for a two-state system is a two-dimensional, complex-valued abstract vector space. This abstract vector space is not physical space. The vector space is not the xy plane. The xy plane is two-dimensional. The abstract complex vector space is two-dimensional, but it is not the xy plane. In some case, a vector in the abstract vector space might have some relation to some position vector in physical space, but you must not think of the abstract vector space as being physical space, nor a mirror of physical space. Generally, it's not. This will be a mental challenge at first. Each such two-state system has an infinite number of states that can be expressed as a linear combination of our choice of a pair of independent, non-overlapping physical basis vectors. So, two orthogonal physical basis vectors selected for the particular physics of that system. The choice of basis states is not unique, though often there are obviously useful choices. We require the two basis vectors to be orthogonal in that they must be physically non-overlapping. There must be none of one basis vector in the other, which is to say there must be zero projection from one to the other. For the basis vectors, this is a matter of physics and the particular system, not math. We choose or declare the two basis vectors to have unit length, unit norm. When the particle is in the state of that basis vector, the particle is wholly in that state. Probability of 1. It is definitely in the state. Therefore, our chosen physical basis vectors are orthonormal, they're orthogonal, and they're normalized based on the physics of the particular system. And for the remainder of this lecture, all vectors and matrices will be representations relative to our predetermined choice of basis vectors. We're leaving the basis vectors arbitrary and abstract. We're not saying what they are physically, but we're saying for any given system, we will select two of them and then we will use them. And that's how we're going to proceed. We are not going to cover how to do a change of basis for state vectors, matrices, or operators. We're not going to do rotations in the abstract vector space. Generally, I'm just going to say basis and leave orthonormal as implicit. So anytime I say basis, I mean orthonormal basis. This is a possible time to take a break. Let's label our basis vectors 1 and 2. We're keeping them abstract, we're keeping them generic, but one of them is going to be the first one and the other is going to be the second one. And we're going to use this notation. We're going to have a ket, a ket 1, and that's going to be a ket of the basis vector 1, or simply the basis vector itself. And we are going to use the column vector representation so that the first basis vector is 1, 0. It selects the first basis vector with none of the second basis vector. The second basis vector will be ket 2, ket e sub 2, e sub 2, or in column vector form, 0, 1. None of the first basis vector, one of the second basis vector. For a particular problem, we must identify and remember the physical states associated with 1 and 2, as 1 and 2 are going to remain abstract. However, just as a sneak peek, in the next lecture, D3, where we're going to do spin 1/2, we will make the basis vectors concrete, and we will change them so that instead of calling them 1 and 2, we will call them z plus and z minus. But we're not going to do that in this lecture. This lecture is not solely or specifically for spin 1/2. It's general, so the basis vectors are 1 and 2. We're also going to define a second form, a dual form of each basis vector called the bra. And we've seen this before, but now we're going to see it more concretely. So we define ket 1, we're also going to have bra 1, and it is going to be a bra of basis vector e sub 1, and it is going to be a row vector 1, 0. And we're going to have bra 2, which is bra of e sub 2, which is the row vector 0, 1. We're going to learn how to use these. So we've seen them in the past without really knowing how to use them. We're going to use them today. This is a possible time to take a break. States in the complex vector space, Part 1. Part 2 will be in this lecture after we cover on the material. So this two-state complex vector space is spanned by or reachable by the two basis vectors. Any linear combination of the two basis vectors is a state vector or just a vector in the vector space. We do not use the term wave function or eigenfunction for the state of a finite dimensional space, such as for two-state systems. We use state vector and eigenvector. So let two states be represented for our chosen basis by the kets u and v being ket u is the column vector with components u sub 1 and u sub 2, which are complex numbers. And in that form, we mean that state ket u is u1 times the basis vector e1 plus u2 times the basis vector e2, but we're going to use the column vector form for the rest of the lecture. Similar for v. It has two components, v1 and v2, both complex numbers. There are corresponding bras to those kets. Bra u is the row vector u sub 1 complex conjugate and u sub 2 complex conjugate. And bra v is the row vector v sub 1 complex conjugate and v sub 2 complex conjugate. Note that the components from the column vector of the ket get complex conjugated to become the row vector of the bra. The row vector of the bra is the complex conjugate of the transpose of the column vector of the ket. The transpose turned the column vector into a row vector, and then we complex conjugated it to get the bra. Now, if any of you know more advanced than I've covered, the bra and the ket are Hermitian conjugates of one another. But don't worry about that. Bras are normally introduced after inner products to develop why they are row vectors and why we need the bra and why the components get conjugated. But I'm just going to present these bras as I've indicated and say we're going to use them and it'll be fine. Now, suppose we have a ket W, which is a linear combination of the kets U and V, with coefficients A and B, which are complex numbers. Then the corresponding bra is bra W is a linear combination of bra U and bra V, but the coefficients have to become complex conjugated, A conjugate and B conjugate. Note the complex conjugates of the factors A and B. You should verify that this is a correct ket to bra conversion using appropriate operations that we've already shown. There's more to say about state vectors for the two-state system after we cover some other material. This is a possible time to take a break. Inner product. We are going to define the inner product of U with V, and it's going to have this symbolism. Left angle bracket, U, vertical bar or pipe, V, right angle bracket. The inner product of U with V of two state vectors, ket U and ket V, represented in our chosen orthonormal basis as the inner product is defined as U sub 1 conjugate V sub 1 plus U sub 2 conjugate V sub 2. Now we can see that also equals the result we would get if we took the bra for U and the ket for V and we multiplied them using correct matrix or linear algebra operations. The bra for U is the row vector U1 conjugate U2 conjugate. The ket for V is the column vector V sub 1 V sub 2. And if we multiply these together, we get U sub 1 conjugate V sub 1 plus U sub 2 conjugate V sub 2. Now let's look at this. So we're saying that the inner product is the bra of U times the ket of V, and what's happening in symbols is if you got rid of the parentheses and you got rid of the dot and you combine the two vertical bars together, that is where the symbolism for inner product comes from. It's like a bra and a ket together, but one vertical bar instead of two. Now, the inner product is a complex number. It's not a vector. It's not a column vector. It's not a row vector. It's a complex number. This is a complex number. U1 conjugate V1 plus U sub 2 conjugate V2, that's a number. All inner products are numbers. The inner product is not symmetric for exchanging U and V. Order matters. Exchanging them complex conjugates the result. Some properties of the inner product, all of which you can verify for yourself, it's not difficult, where alpha and beta are complex numbers. If you reverse the order, if you start with U inner product V and you want to know what V inner product U is, you take U inner product V and you complex conjugate it. Now, if the ket is a linear combination of other kets, we can pull those linear combinations apart, and we get this result. The coefficients alpha and beta come out as they are. So we can pull out the coefficients alpha and beta unchanged and use the inner product of u and v and u and w. We don't change the order, and u is still on the left on the bra side. Now, if the bra was a linear combination of other bras, we can do the same thing. However, when we pull the coefficients out, we must complex conjugate them. So we get an alpha conjugate and a beta conjugate. And again, we don't change the order. The v was the ket and in the inner product, and it remains the ket in the inner product. This is a possible time to take a break. We define the length or norm of v, of state vector v, as the square root of its inner product with itself. So here we have the inner product, v with v, we take the square root of it. We have the definition of the inner product, so v1 conjugate v1 plus v2 conjugate v2. We know that this is the same as the square root of the square of the magnitude of complex number v1 plus the square of the magnitude of complex number v2. The magnitudes are real numbers, the squares are positive real numbers, so we are going to end up with the square root of a positive or non-negative real number. So the norm is a real non-negative number, and it's only 0 for the 0 vector. We can normalize a non-zero vector by dividing its components by their original norm. So if we start with a vector v1, v2, its norm will be square root of magnitude square of magnitude v1 plus magnitude squared of v2. If we divide both components, the top and bottom components, by that square root, the result is normalized. If you take the norm of this vector, you will find that it is 1. Two vectors u and v are orthogonal if and only if their inner product, u with v, is 0. And if it is 0, then it is unchanged. If we were to reverse the order, the inner product of v and u, that would be the complex conjugate. Complex conjugate of 0 is 0. You can see that the column vector representations 1, 0, and 0, 1 of our basis vectors, they are orthogonal to one another, and they are normalized. If u and v are normalized, then the inner product of u with v tells how much of state u there is in state v, their overlap. The inner product of u with v is said to be the probability amplitude, or just amplitude, for a particle in state v to be found in state u, which is generally a complex number. But this is not yet the probability, which we cover in the next section. So a little beware that there's a term probability amplitude, and then there's the term probability, and those are different. And we have to live with that. This is a possible time to take a break. Probability. There's two cases for probability, and we will handle them both. If u and v are both normalized, then the square of the magnitude of their inner product, remember their inner product is their probability amplitude or just amplitude, the square of the magnitude of their inner product is interpreted to be the probability that a particle in state V will be found to be in state U if a measurement is taken. I should say is. Now, there's a different case. If we are running some experiment and we start out with a normalized input, and then we look at different output states that are not necessarily normalized, they're generally non-normalized, we want to know the probability of the particle appearing in output state 1 or output state 2. So let's look at that. For a non-normalized output state, V, of a single particle experiment, we define the probability of V of the particle being in state V, or equivalently of the state being occupied by the particle, if and when we do a measurement or a detection. That probability is the inner product of V with itself, which is equal to the square of the norm of that state vector. And this is a real number. A normalized state has probability 1. Its inner product is 1. The particle is completely in that state. The zero state, 0, 0, has 0 probability for the particle to be found in that state. A state with norm 1 over square root 2 has probability 1/2 for the particle being found in that state. Now, probability is independent of the overall phase of the state vector. Overall phase means a phase applied to both components. If we multiply the ket, any ket, by a phase e to the I alpha, then the bra would have to be multiplied by e to the minus I alpha, the complex conjugate. And when we do the inner product, those phases will cancel. So the overall phase does not change the norm of the vector, and so it does not change the probability. Now, negating a ket is just a particular instance of phase, and so it does not change the inner product. Now, this way of handling probability is different than how probability was handled for spatial problems. In spatial problems, we calculated probability density, and we always normalized a state so that the probability density would be meaningful. There's no probability density here, just probability for being in a state. For two-state systems and for other finite-dimensional systems, every state but the zero state is normalizable. But we do not choose to normalize every state that is normalizable, unlike when we did spatial problems. Instead, the state of the input to an experiment will be normalized. We will normalize those, and we will see the probabilities of different output states of the system. Or the initial state of a system will be normalized, and then we would see the probabilities of different measurements of the system. If we normalized everything, we would lose all our probability information. We don't want to do that. Probability information is very important in understanding what's happening. So the probability for some output state is conditional on the input state, but we're not going to use the mathematical language of conditional probability here. We could, but we don't. We just keep track of, okay, it was normalized here, and let's see what the probability is here. This all works out fine. It works out as you expect. It's not that complicated, and it's easy to get used to. Unless if you're a mathematician who specializes in probability, you will You will think in terms of conditional probability, and that's fine, that's up to you. We will see how this works in the next lecture, D3, for spin 1/2 particles. Now we're going to have at most one particle in a state. We're not going to deal with counts of finite numbers of particles sent into an input or measured, by some observable at some output port. We're going to consider that one particle gets sent into an input, and it has specific probabilities for exiting different outputs or being a particular result of some measurement. Now, it's true that whenever we have probability, we have to accept that experimentally, probability between 0 and 1 does not tell us what the result of a single measurement will be. The probability speaks to the tendency of the average result of very many trials on the unchanged systems with inputs prepared in exactly the same state. That part is the same as for spatial problems. So, nevertheless, we speak of a single particle and the probabilities of different states, outputs, or measurements, and it works really well. So that's what we're going to go with. This is a possible time to take a break. States in the complex vector space, part 2. Let's continue with our states now that we have some more mechanism to work with. Now we're going to let ket v be an arbitrary normalized state vector. And we're going to choose to write its components as complex exponentials. We can do that. You can write any complex number as a complex exponential, so that's fine. So the first element, the first component, we're going to have be r e to the I gamma, where r is a real number and gamma is a real number. We're going to divide that by a denominator, talk about that in a second. The second component, we're going to have s e to the I delta. Now, e to the I gamma and e to the I delta, those phases, gamma and delta, are real numbers, so the complex exponential is only a phase. So in terms of normalizing, we only need to do the square root of r squared plus s squared. So this is normalized. Now, you might notice that, look, in the first component we have r over square root of r squared plus s squared. In the second component we have s over square root of r squared plus s squared. This looks a lot like sines and cosines in trigonometry. So let's leverage that. Let's replace r over this. So in that scenario, r and s would be like perpendicular legs of a right triangle, and square root of r squared plus s squared would be the hypotenuse. So if we take r over the hypotenuse, we'll call that cosine of an angle alpha, whatever the angle has to be to make that number be work out, and sine of alpha as s over the hypotenuse. If you square this plus square that, you get 1, that as you would, because it's normalized. Now, r and s could be any real numbers, positive or negative, so for the moment, alpha could range anywhere from 0 to 2 pi, anywhere in the plane. So let's rewrite our ket v that using those. So ket v is cosine alpha e to the I gamma, and the second component is sine alpha e to the I delta. And that's helpful. Now we have 3 numbers. And they're actually 3 angles. So that's interesting, and we can make a little progress yet. Let's pull the phase out of the first component so that we end up with a common overall phase, e to the I gamma. In doing that, we have to adjust the phase in the second component. We'll do that by defining beta as delta minus gamma. So we get that ket v, the same ket v, we haven't changed ket v, is e to the I gamma times a column vector that is cosine alpha and sine alpha e to the I beta. So normalized state vectors can be fully specified by 3 angles, and we can choose those angles to each be in the range 0 to 2 pi if we want. But we can do better than that. It turns out, as we will see in different points in this lecture, that the overall phase, in this case, that e to the I gamma that we pulled out, it does not affect the norm of the vector. It does not affect the probability of the vector. It will not affect any observable of the system. So we can choose to remove it without loss of generality. When we remove it, we have changed the vector in the vector space, but we've changed it to a vector which is totally equivalent in terms of the physics of the system. And that's fine to do and useful to do. Now, because the overall phase does not matter, we can also limit the range of alpha. Alpha was originally 0 to 2 pi, which would allow, the numerator could be positive or negative. I'm sorry, not numerator. The first component could be positive or negative. The second component could be positive or negative. But in terms of unique vectors, after we remove the overall phase, we can limit ourselves to the first quadrant for alpha. So alpha 0 to pi over 2. And that'll give us all of the state vectors that we need to figure out the physics of any two-state system. So we can choose to write the general normalized state vector knowing that we don't care about the overall phase. We could choose to write it as ket v. Now this is actually a new ket. I could have called it ket w or whatever, because I have changed the overall phase, but I know it's equivalent. So this ket is physically equivalent, quantum mechanically equivalent to the earlier ket v, even though mathematically it's not identical, because I have removed the overall phase term. So equivalent ket v is cosine alpha for the first component, sine alpha e to the I beta, where alpha, now we're restricting to 0 to pi over 2, and beta could be any number, but we will normally try to keep it in the range 0 to 2 pi. Now, since we know that the overall phase does not change the physics, if we needed to, we could change the phase of this. Sometimes it's better for us to move the phase from the second component to the first component, and we do that by changing it from e to the I beta in the second component to e to the minus I beta in the first component. So this will be our standard form with the complex exponential in the second component. If we need to, we'll use the alternate form. So aside from an arbitrary overall phase, normalized state vectors can be fully specified by 2 angles. And let's note that for physical three-dimensional space, and starting with a choice of Cartesian axes, direction in space can be fully specified by 2 angles: the polar angle and the azimuthal angle, theta and phi. This is going to be important for spin 1/2 particles in the next lecture, D3, but we're not going to use it here. In this lecture, we're going to use this form, alpha and beta. This is a possible time to take a break. Hermitian operators, observables. In quantum mechanics, observables are always Hermitian operators. When we covered spatial problems, I did not define Hermitian for you for those continuous operators. I kept saying, oh, this is a Hermitian operator, and I never told you what the definition for Hermitian is because it involves a little more mathematical framework than I really want to take you through an introductory course, and you didn't really need to know. The only thing you've needed to know up to this point is whenever I told you something was an observable, I also told you it was a Hermitian operator. We didn't actually use the Hermiticity before now, but we will for the two-state system, and so I need to define Hermitian for you, and we will do that for the two-state system, but you'll see that it obviously applies to any finite dimensional vector space. And the operators in a finite dimensional vector space, they're always square matrices. So we're dealing with two-state systems, so let matrix M be the following 2 by 2 complex matrix representation relative to our predetermined orthonormal basis. So M is a 2 by 2 matrix, 2 rows, 2 columns, 4 elements. The elements have 2 indices. The first index is the row number, the second index is the column. So 1, 1 is first row, first column, 1, 2 is first row, second column, 2, 1 is second row, first column, 2, 2 is second row, second column. All 4 of those numbers are complex numbers. So it takes 4 complex numbers, or equivalently 8 real numbers, to identify a particular 2 by 2 matrix. Now, matrix M is a linear operator on the two-dimensional complex vector space of the two-state system. Let's have state vector V be V1, V2. We can multiply matrix M to the left of vector V. Maybe you are familiar with how to do this operation from linear algebra. Maybe you're not. If you are, great. If you're not, just take my word that this is the definition for that multiplication. So if we multiply M to the left of V, M is this matrix. We saw that before. V is this vector. We saw that before. The result of multiplying them together is this column vector. The first component is M11 V1 plus M12 V2. The second component is M21 V1 plus M22 V2. 2 rows, 1 column, it's a column vector. Complex numbers, it's a vector in the abstract vector space. It's a ket. The result is a 2-element column vector, and so is some state vector or ket in the vector space. The matrix operator M operating on the state vector V produces another state vector in the vector space. Operator M is linearly because you can easily show, we're not going to show, it's very easy to show that if you operate matrix M on a linear combination of vectors, AU plus BV, if you just use the multiplication that I gave you there and you move things around with algebra, you find that the coefficient A comes out, the coefficient B comes out, and we end up with A times matrix M multiplied by vector U plus b times matrix M multiplied by vector v, where a and b are complex numbers and u and v are vectors in the vector space, and that is what a linear operator does. So every 2 by 2 matrix M is a linear operator. This is a possible time to take a break. Now we're going to define a thing called the transpose M superscript T, capital T, of matrix M. The transpose is take the original matrix, exchange the rows with the columns, and that's the transpose. So it used to be that the first row was M11, M12, but now that's our first column, M11, M12. Our second row used to be M21, M22. Now that's our second column, M21, M22. MT is the transpose of matrix M. From that, we're going to define the Hermitian conjugate M dagger, as we call this M dagger, of M, as the complex conjugate of the transpose of M. We already know what the transpose is, so we just need to take the transpose and conjugate it. Here's the transpose, here's the conjugate of the transpose. M11 star, M21 star, M12 star, M22 star. That is the Hermitian conjugate, M dagger, of M. The Hermitian conjugate is also called the adjoint, the Hermitian adjoint, or the Hermitian transpose. Now, if you're a mathematician, you might say, well, an adjoint is a little different than a Hermitian conjugate, and that may be mathematically true. They're the same in the reality of quantum mechanics use of mathematics. So when a matrix M is equal to its Hermitian conjugate M dagger, then we call that matrix Hermitian. So that's our definition of Hermitian now, but only for matrices, not for spatial problems with differential operators. So when will that be true? That will be true. So M must be equal to M dagger. Well, here's M dagger. When will M be equal to it? Well, M11 will have to be equal to M11 star. M22 will have to be equal to M22 star. So those two, they must be real. Real numbers, when you conjugate them, they are unchanged. So M11 and M22 must be real. And the other two numbers, M12 and M21, must be conjugates of one another, complex conjugates of one another. M12 and M21 must be complex conjugates of one another. When those things are true, matrix M is Hermitian. Such a Hermitian matrix is described by 4 real numbers, not the original 8 real numbers of the original 4 complex numbers. Why 4? Well, M11 and M22 are real, so that's 2 numbers. M12 and M21 are conjugates of one another, so we could pick one. We could pick M12. It can be any complex number, so it requires 2 real numbers to describe that. So we need 2 real numbers for this diagonal and 2 real numbers for the off diagonal. This is a possible time to take a break. Now, why do we care about all this Hermitian stuff? Because an observable in quantum mechanics must always be a Hermitian operator. Observables of a system can be measured, at least in principle. And if measured, the result will always be a real value. So we're not going to be interested in every possible matrix M. We're going to be interested in matrices that are Hermitian, because then they can be observables that we could measure. So instead of calling it M, we'll call it O for observable. Let observable O, which is a matrix, be the most general Hermitian matrix for the two-state system with respect to our predetermined basis. We can write this in various ways, but we're going to choose to write it as follows. This 1, 1 element has to be real. It can't be complex. We're going to choose to write that as the sum of two real numbers, A plus D. Element 2, 2 also has to be real. We're going to choose to write that as the difference of those two, A minus D. We'll see why in a moment. This helps us going forward. So it might look complicated right now. Why didn't we just call them, why didn't we call this one thing and this another thing? There's a reason why we do this. We'll see it in a second. Element 1, 2 must be the complex conjugate of element 2, 1, and we can get that with two real numbers by making 2, 1 be B plus IC, where B and C are real numbers. And then the complex conjugate is just B minus IC. So this is Hermitian. You should verify that it is Hermitian. You should think about how this is completely general, that every Hermitian matrix can be expressed this way. Since it's Hermitian, it's an observable. It's a quantum mechanical operator. We could choose to write it O caret, O hat, with a caret over it, as we did for spatial operators in earlier lectures, but in this two-state context, there's no confusion. So we're just going to write it as O, and it is an observable operator. It's a 2 by 2 Hermitian matrix. So we can dispense with the caret as long as we understand this. So let's keep that general form, but we're going to rewrite it as here on the right in terms of 4 matrices. Now, why are we taking one matrix and writing it in terms of 4? There's a reason for it. We will see that in a little bit. So if this seems like we're going in an odd direction, trust me, we're going in the right direction. So here, A, B, C, and D are real numbers. This I is the identity matrix, 2 by 2 identity matrix, 1, 0, 0, 1. And when we multiply A times that, we get an A here and an A here, and which is that A and that A. These other 3 matrices, sigma 1, sigma 2, sigma 3, they're very special matrices. If you want to pause, you can figure out what those matrices are just by saying that this equals that. Maybe you want to do that, or maybe you just want me to tell you. Sigma 1, sigma 2, and sigma 3, they are called the Pauli matrices after Wolfgang Pauli, and they are as follows. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. Sigma 3 is 1, 0, 0, minus 1. Now, you might look at this and say, why do I care? This is complicated. You started with one matrix, you got 4, why are we doing this? We're doing this because this is the way to unlock the secrets of two-state systems and spin 1/2 systems. Once you know this, after this lecture and the next lecture, It's very easy to say, oh, well, it's obvious, that this is definitely the way to do it. This is great. It makes everything clear. Until you get to that point, you just have to follow along and you will start to see why it's good. The Pauli matrices are the standard decomposition of the general observable and will be very helpful to our understanding of spin 1/2 systems in lecture D3. The final section of this lecture, D2, will explore all the properties of the Pauli matrices. In fact, we're going to see that all the properties of them stem from two-state systems. Spin 1/2 inherits that, but spin 1/2 doesn't give the Pauli matrices their property and their power. Two-state systems generate Pauli matrices. This is a possible time to take a break. Now, operators are not generally commutative in quantum mechanics. Operator 1 operating on operator 2 is not generally the same as operator 2 operating on operator 1. When we say operating is always from the left. So generally, order matters. Your first impression might be this is weird, it's complicated, and it is at first, but this non-commutativity of operators and matrices, it's actually essential to quantum mechanics. It's essential to Heisenberg's uncertainty principle. It's essential to orbital angular momentum, which we didn't study, in our lectures. It's essential to intrinsic spin angular momentum, which we are studying now and in the next lecture. Matrix multiplication is non-commutative, order matters. And this is great. This allows us to use square matrices to represent quantum mechanical operators in finite dimensional vector spaces, and it all works out just great. And it's not that hard. It's not that complicated. We'll see this non-commutativity for the Pauli matrices at the end of this lecture. Now, whether two observable operators do or do not commute is important for any particular system. When two observables do commute, they share the same set of eigenvectors. The same set of eigenvectors applies to both. And when that happens, that's great. That lets us see that two aspects of a system are compatible. But other times, two observables don't commute. They don't share the same set of eigenvectors. And if you measure one observable and you get an output state from that, that collapsed state is going to change when you measure it by the other observable. We know it's going to change because the observables did not commute. Not commuting means that measuring either after the other will change the system. It's part and parcel of what not commuting means. We're going to see this applies for the Pauli matrices. They do not commute. And that is important. This is a possible time to take a break. Now we're going to be interested in the eigenvalues and eigenvectors of any observable O that we're interested in. Well, what are eigenvalues and eigenvectors? We talked about this earlier in the course. We did, eigenvectors and we did functions and eigenvalues of the Schrodinger equation. But here it's similar but a little different. We're going to take operator O, and when we operate on some state, we'll call it psi, ket psi. If operating on that produces ket psi times some number, when that happens, we call lambda an eigenvalue, and there are two eigenvalues for an operator O for a two-state system. They could be the same, they could be different, but there are two, so it can't be three. When they're the same, we say that there are two with the same value. When we can solve this eigenvalue equation, lambda will be the eigenvalue, and the particular state vector psi that solves it is called the eigenvector corresponding to that eigenvalue lambda. We'd like to know how to solve that. And actually it is easy to solve. Requires a little linear algebra, but the least amount of linear algebra that you could possibly have. So we could take the right side and move it onto the left side by doing a subtraction. We would get O psi minus lambda psi equals 0. And we can combine that so that we get one operator operating on psi equals 0. Now that operator is O minus lambda times the identity matrix. So that's just from subtraction. Now it turns out from linear algebra that the way to solve this, there's an easy way to solve it. You may or may not ever have seen it. You can just trust me. We're not going to prove why it is a solution. You could check it, but easier if you just trust me. We can solve for the two eigenvalues of lambda by solving this determinant. You may not know what a determinant is. That's okay. Don't worry about it. The determinant of the matrix O minus lambda I equals 0. Now notice psi went away. If we can find the solution for this determinant that does not involve psi, then we get the eigenvalue lambda. And once we have lambda, we can find the eigenvector psi. So what is O minus lambda I? Well, we know what O is. It's A plus D here, A minus D here, B plus IC, B minus IC. But we have to do minus lambda I, which means we need a minus lambda on the 1, 1 element and a minus lambda on the 2, 2 element. And we take the determinant of that. Now, you might not know what a determinant is. Don't worry about it. A determinant is when you take this element times this minus this element times that. We get this equation. You could check it if you want, or you can just trust me. You could do some math, and then you get this equation, and you can solve it with the quadratic. It's a quadratic equation, and we know how to solve quadratic equations. We get this solution. Lambda equals A plus or minus square root of D squared plus B squared plus C squared. And remember, all of A, B, C, and D are real numbers. None of them are complex. So these are the two eigenvalues. Called them lambda plus when we have a plus sign, lambda minus when we have the minus sign. These are the two eigenvalues of Hermitian observable O in our given basis. D is real, B is real, C is real. So inside the square root is a real non-negative number. It could be 0. It's either 0 or positive, can't be negative. So we don't get any imaginary or complex numbers out of this. We get two real eigenvalues. The two eigenvalues of any general observable are real. The two eigenvalues represent the two possible results of a measurement of operator O on states of this system. Why are there two possible results? Because we're dealing with a two-state system. When we do a measurement on this system, if we get the first eigenvalue, lambda plus, then we will end up collapsing to the state, the eigenvector associated with lambda plus. If the measurement produced the eigenvalue lambda minus, then we will have collapsed to the state of the eigenvector for lambda minus. Now, these eigenvalues apply to any Hermitian matrix. The Pauli matrices are Hermitian. If I didn't mention that, I'm going to mention that now. They are Hermitian. You should verify that. And so we can find the eigenvalues of the Pauli matrices, and you should do that. And they're always plus or minus 1, and that's important to why we choose the Pauli matrices that way. It turns out that the two eigenvalues of an operator are independent of our choice of basis vectors, but we're not going to prove that. This is a possible time to take a break. For a given specific problem, we solve for the two eigenvalues, and then we can determine the two corresponding eigenvectors in that predetermined basis. We're not going to show how to do that. It's not hard to do. We're not going to do that in general. We will do that for specific problems. Then the eigenvalues and eigenvectors are used to solve the problem. If the two eigenvalues differ and they're non-zero, then the two corresponding eigenvectors will be orthogonal, which we're also not going to prove. Now, if the observable is actually a Hamiltonian, a time-independent Hamiltonian, then the observable gives us an energy observable, and we could get one degenerate energy eigenvalue of E equals A when all of D, B, and C are 0. But if any of them are non-zero, then we get two non-degenerate energy eigenvalues. If B and C are very small compared to D, then the two energy eigenvalues are approximately A plus D and A minus D. If D and C are very small compared to B, then the two energy eigenvalues are approximately A plus B and A minus B. In a lot of two-state systems, we end up with energy splitting. We end up with, some external something, an electric field, a magnetic field, something, that when we turn it on, it can take a single energy level and split it into two. And you can see that, so A is like the value with the external field shut off, and then the external field is either B or D, and then it splits the levels. If we have a time-independent Hamiltonian and we solve for its energy eigenvalues and energy eigenfunctions, we can then determine the time evolution of a state from an initial state, just as we did for spatial problems, starting with the time-independent Schrödinger equation and then using time evolution. We're not going to do this for two-state systems, but it's not that difficult to do. And it can be used in problems to show how nuclear magnetic resonance works and how lasers work. We're not going to do that, however. In fact, we're not going to solve for any energy eigenvalues of two-state systems, but we will use spin-angular momentum operators and their eigenvalues and eigenvectors in the next lecture, D3, on spin 1/2 particles. This is a possible time to take a break. I hope I haven't lost you to this point. It's general, which has the advantage that it can be used in very many problems, but it has the disadvantage that you might not see where we're going with it and why you should continue to listen to me and check equations when you don't know what they're going to be used for. But we will get there. Expectation values. Let O be this operator in the form that we've already discussed it. It's an observable operator, a Hermitian matrix. Let U, V, and W be normalized state vectors. We can define the sandwich or the matrix element as follows. So a sandwich looks like an inner product, but it's got something in the middle of the sandwich. So there's meat in the sandwich. So this looks like bra U, operator O, ket V. And in fact, that is exactly the meaning of it. If we use those as vectors and matrices, that is exactly what we mean the operation to do. We mean bra U, which is a row vector, times matrix O, which is a 2 by 2 Hermitian matrix, times ket V, which is a column vector. We can mathematically, so operator O operates on vector V, ket V, and we already know how to multiply a 2 by 2 matrix times a 2 by 1 column vector. So we just do that. We substitute in that result from, we've had that already. And now we have a 1 by 2 bra row vector. And this is just a 2 by 1 column vector. We said before that if you take a 2 by 2 operator and operate on a state vector, you get a new state vector. Well, this is the new state vector. Well, we know how to multiply a 1 by 2 bra row vector times a 2 by 1 ket column vector. We just do that math and we end up with this result. Now, if you look at this sandwich, it's linear in the second state vector, the ket. If the ket had another factor on it, that factor would be unchanged in this result. But it's antilinear in the first state vector, the bra, because if there was another factor on the bra, it would have to be complex conjugated in the output. So that's called antilinear. And here are equations to show what we mean by this linearity and antilinearity of the sandwich or the matrix element. This is a possible time to take a break. Now we're going to define the expectation value of observable operator O for normalized state vector V. The expectation value for operator O in state V is the sandwich or matrix element, but with U replaced with V. So it's the sandwich VOV. So we just substitute in V1 instead of U1 and V2 instead of U2. Now, this might seem like a mess. Mathematically, we are going to shift it around to look like this. You might say this looks like a mess, but it's actually not. Importantly, A, B, C, and D appear only once here. A appears and gets added to the rest. D appears and it gets multiplied by the magnitude of V1 squared minus the magnitude of V2 squared, which means that if V1 and V2 had equal magnitude, this D component would go away. B gets multiplied by twice the real part of V1 star V2, and C gets multiplied by twice the imaginary part of V1 star V2. It looks complicated, but it has some useful properties for us. A, B, C, and D, they're always real. Magnitude squared is real. The real part is real. The imaginary part is real. So the expectation value of this general observable is always a real value. We've said before that observables will have, every measurement will be a real value, and this bears that out. The expectation of value of an observable, it's independent of the overall phase of a state vector. The overall phase, so a phase applied to both V1 and V2, it would cancel out of magnitude squared, and it will cancel out of V1 star V2 because it's present in both, but one of them gets complex conjugated. So overall phases do not affect expectation values. In the final section of this lecture, we're going to find that the normalized eigenvectors of the Pauli matrices are as follows. Aside from an arbitrary overall phase, which we just said does not change the expectation value. Pauli matrix sigma 1 has eigenvectors 1 over square root of 2 times 1 in the first component and either plus or minus 1 in the second component for the two eigenvalues, the plus and minus eigenvalues. Now, so in this case, the magnitude of both components is the same, which means the D portion is going to go away, and they're both real, so the C portion is going to go away. This is going to go away because this magnitude and this magnitude are the same for the eigenvectors of Pauli matrix sigma 1. This is going to go away because there's no imaginary part, so we're going to end up with this B part. For sigma 2, the eigenvectors are 1 over square root of 2, 1 for the first component, plus or minus I for the second component. This is going to produce the C portion of the expectation value. Pauli matrix sigma 3 has eigenvectors 1, 0, and 0, 1. This produces the plus or minus D portion of the expectation value. These results are applicable to any two-state system. We have not invoked any assumption or property unique to spin 1/2 systems in this lecture. If you want more advanced material and you'd like to read the MIT OpenCourseWare 805 lecture notes on two-state systems, those lecture notes are here at this link, but they do use some material we have not covered, and probably you should watch lecture D3 on spin 1/2 before you go to these lecture notes. You don't have to for my course. This is only for people who want to jump ahead to the MIT course. This is a possible time to take a break. Now, matrix multiplication. We do need to know how to multiply two 2x2 matrices together for a couple cases. So multiplying them together represents a sequential application of their operators. So let's take matrix M and matrix N, the product M to the left of N, which applies matrix N to some vector to its right, and then matrix M onto that. It's this following 2 by 2 matrix. If you're familiar with matrix multiplication, you will instantly see that this is the result. If not, you'll have to take my word for it. If we reverse the order, n to the left of m, we would get a different matrix, a different result. Matrix multiplication is generally generally non-commutative, and so are quantum mechanical operators generally. Now there's one other thing we can do. We can multiply a ket u, which has the representation of a 2 by 1 column vector. We can multiply that to the left of a bra w, which is a representation of a 1 by 2 row vector. Ket u, bra w, ket u times bra w, column vector times row vector, two by 1 by 1 by 2, we end up with a 2 by 2 matrix, this 2 by 2 matrix. If you know how to multiply matrices together, you'll see that this is the answer. Otherwise, just accept this as the answer. We get a 2 by 2 matrix. It's generally not going to be Hermitian. The elements will be complex numbers. Now, if this is unfamiliar to you and you are uncomfortable with that and you want some help, I'm sure you can find short tutorial videos at Khan Academy. They'll use real numbers, not complex numbers, but they'll show you how to multiply matrices together. This is a possible time to take a break. Orthogonal projectors. This material on orthogonal projectors and Pauli matrices is duplicated unchanged as lecture video D2B, as well as the final part of lecture D2. This is because some people might want to just find it on YouTube by searching for Pauli matrices. But if you've watched it in one place, you don't need to watch it again. For a two-state system, let ket u and ket v be an orthonormal pair of state vectors, not generally the basis vectors, just state vectors. And let w be an arbitrary state vector, not necessarily normalized. We're going to define orthogonal projectors, p sub u and p sub v, as follows for the state vectors ket u and ket v. So the projector p sub u is defined as ket u times bra u. And we just saw in the prior section how to multiply those together. So this is the result. And this is the result for v instead of u. Now, u1 star, that's magnitude of u1 squared, that's a real number. u2 star, also a real number. Notice that these other two, they are complex conjugates of one another. u2 is unconjugated here and conjugated here. u1 is conjugated here and unconjugated there. So they're complex conjugates of one another. So every projector is a Hermitian operator, and so it is an observable. I believe that the sum of these two projectors, p sub u plus p sub v, equals the identity matrix, because u and v are orthonormal and overall phase is arbitrary. Let's see what the p sub u projection of or on or onto state vector ket w would be. So projector p sub u operating on ket w. P sub u is an operator, We could put it to the left of a ket, and that operates on the ket. So piece of u is ket u bra u, and that's going to operate on ket w. Well, that's the same. That's identical to bra u and the inner product of u with w. That's what this bra and this ket do. They produce this inner product. And once we see that it's an inner product, it's just a number, and we could move the number to the left of the ket if we want. So we get this inner product, this number, times ket u. So this is a state vector parallel to ket u with a magnitude and sign equal to the amount of u that is in w, their overlap. If u and w are orthogonal, no overlap, the projection will be 0. The inner product will be 0. The projection will then be 0. If w is some complex number times u, then when we plug, then the inner product is going to be alpha, and the projection will be alpha times ket u. We will use these projectors in the Pauli matrices and in the next lecture, D3, on spin 1/2 states. This is a possible time to take a break. Pauli matrices. We introduced them earlier, sigma 1, 2, and 3, Pauli matrices. If you're comparing against some other material, a book or a class, you might see, probably will see, the subscripts as being x, y, and z instead of 1, 2, and 3. That is true for the specific choice of basis vectors as z plus and z minus for a spin 1/2 problem, and we will use this in lecture D3 for spin 1/2 particles. But here we're talking about general generic two-state systems. So we said our basis vectors will be orthonormal, but we haven't chosen any directions in space. So we should stick with 1, 2, and 3, not x, y, and z. Now, a lot of books and classes, they teach you spin 1/2 first. And so, they're going to call them sigma x, sigma y, and sigma z. And that's fine, but we're choosing to do generic two-state systems first. So we're using 1, 2, 3, not x, y, z at this point. For the remainder of this lecture, when we use I, J, and K as indices, subscripts, they can take on any value 1, 2, or 3. The Pauli matrices have many properties. They're all easy to prove because 2 by 2 is a pretty easy system to work with. You should verify these results for yourself, but I'm not going to verify them with you. Try it yourself. The trace of a matrix, any square matrix, is the sum of the main diagonal, the elements on the main diagonal. So the trace of a 2 by 2 matrix is the sum of M11 and M22. And that is 0 for all 3 of the Pauli matrices. A result in linear algebra says that therefore the 2 eigenvalues of each Pauli matrix are going to sum to 0. The determinant of each Pauli matrix is -1. If you don't know how to do a determinant, don't worry about it. We're not actually going to need it. The eigenvalues are plus 1 and minus 1, and they sum to 0. If you know how to get, well, we already showed a formula for how to get the eigenvalues, and so you just have to plug in, and you will be able to verify that the eigenvalues are plus or minus 1. Now, we need to discuss the normalized eigenvectors of each Pauli matrix. But I'm not going to show you the procedure for how to solve for the eigenvectors. If you already know how to do this, great. If you don't, just trust me, or you'll be able to verify that they're eigenvectors without solving for them. Verifying them is not difficult. So I'm going to give you the normalized eigenvectors of each Pauli matrix, unique only to within an overall phase that we don't care about because it doesn't affect the physics. So in the following table, we're going to associate 1 with x, 2 with y, and 3 with z, only to anticipate that we want to use these results in the next lecture, D3, on spin 1/2 particles. Though if we're not talking about a spin 1/2 particle, we should just stick with 1, 2, 3. Now beware, here we're going to use ket 1 and ket 2, but here 1 and 2 mean the first and second Pauli matrix. We don't mean the first and second basis vectors of the two-state system, so don't confuse that. This is a possible time to take a break. For Pauli matrix sigma sub 1, which for spin 1/2 is sigma x, it has 2 eigenvalues, plus 1, minus 1, no surprise. I'm going to tell you that the normalized eigenvector for the plus 1 eigenvalue has this representation: 1 over square root of 2 times the column vector 1, 1 in our choice of basis. And we give that the name, the ket name, 1 plus or x plus. Now, you could verify this. You could take this matrix and multiply it to the left of this vector, and you would get out this vector unchanged, which is to say this vector times plus 1. So you could check that this is a correct eigenvector without knowing how to find it in the first place. Now, we're going to use, for the minus eigenvalue, we're going to use this eigenvector, 1 over square root of 2, 1, minus 1. If you were to take this matrix times this vector, you would get this vector out, but multiplied by minus 1. It is true, and you should verify, that the x plus and x minus eigenvectors are normalized and they are orthogonal to one another. Now, for sigma 2 or sigma y, eigenvalues plus or minus 1, the y plus eigenvalue, 1 over square root of 2, 1i, the y minus eigenvector, 1 over square root of 2, 1 minus I. These two eigenvectors are normalized and they are orthogonal to one another. Not orthogonal to the x ones, but they are orthogonal to one another. Sigma 3, sigma z, eigenvalues 1 and minus 1. Eigenvectors 1, 0 and 0, 1, which we call z plus and z minus. These pair of eigenvectors, they are normalized and they are orthogonal to one another. Not to x or y, but to one another. Notice that the two eigenvectors of a Pauli matrix are orthogonal. Now that we have the eigenvectors, we can, if we choose, rewrite the Pauli matrices in terms of the difference of orthogonal projectors as follows. And we'll use the x, y, and z notation, not the 1, 2 notation. If we constructed the projector for x plus, which is CAD x plus bra x plus, and we constructed the projector for x minus, which is CAD x minus bra x minus, and we subtracted the second one from the first one. If you do that as a matrix operation, you will find that that exactly equals sigma x. And you will find the same thing for sigma y using the y projectors, and the same thing for sigma z using the z projectors. If you change it a little bit, instead of doing a subtraction, if you add them, we find that every case adds up to the identity matrix. This is a possible time to take a break. Now we know what the Pauli matrices are. What if we multiply one Pauli matrix times itself? If you do that, you will find that you always get the identity matrix. So every Pauli matrix is its own matrix inverse. And this is consistent with why the eigenvalues are +1 and -1. The Pauli matrices are also Hermitian, and so if they're Hermitian and they are their own inverse, they also are what is called unitary. Their Hermitian conjugate is their inverse. We're not going to need that in our course. Now let's multiply two different Pauli matrices together. If you multiply sigma 1 to the left of sigma 2, you would find out, or will find out, that that is exactly Pauli matrix sigma 3 multiplied by imaginary number I. And if you took sigma 2 times sigma 3, you would get I times sigma 1, and if you did sigma 3 times sigma 1, you would get I times sigma 2. But if you reverse the order, instead of doing 3 times 1, you did sigma 1 times sigma 3, you would get minus I sigma 2, and so on. So there's a lot of order and pattern in these Pauli matrices, and it directly relates to angular momentum. We don't know that yet, but it does. There's a shorthand for writing all 6 of these in one equation. The shorthand requires you to learn something new. You could say, well, why do I want to learn that? Why don't I just use those 6? Either way, if you want to know the shorthand, you will see it in books. Every book that shows you the multiplication of Pauli matrices will show you this shorthand, so I might as well show it to you. Let I, J, and K be any elements, of 1, 2, or 3. If you multiply Pauli matrix sigma sub I times Pauli matrix sigma sub j, you will get a Pauli matrix sigma sub k multiplied by pure imaginary number I. Notice that this I is not the index I. But then there's this funny symbol, epsilon ijk, which is called the Levi-Civita symbol, the permutation symbol, the antisymmetric symbol, or alternating symbol. And it has this rule. Epsilon ijk is +1 if ijk is 1, 2, 3, 2, 3, 1, or 3, 1, 2. It's -1 if ijk is 1, 3, 2, 3, 2, 1, or 2, 1, 3. It's 0 if any of them are repeated. I equals j, j equals k, or k equals I. So the value is +1 for even permutations of 1, 2, 3. 1, 2, 3, if you rotate them 1 to the left, you get 2, 3, 1. If you rotate it once again, you get 3, 1, 2. It's -1 for odd permutations, and 0 if any index is repeated. Now, if you want to say, no way am I going to remember all that, just so that I can write 6 equations as 1, but then I have to remember this funny symbol. If you don't like this symbol, that's fine. You're not going to need it for this class. But if you were to look at a book or another class, you would definitely use that symbol. That's how things will be written. So beware that, that unsubscripted I was not an index or a subscript. It was the imaginary unit. You could say, gee, we shouldn't have used I as an index or a subscript if we knew we were going to use I as an imaginary number to avoid confusion, except everybody does it this way. So every book will do it this way. So that's the way you need to see it. I wouldn't be doing you any favors if I didn't call it I, because then you would look in a book and you'd be confused. This is a possible time to take a break. The commutator of A and B, which we write as square bracket A comma B square bracket. The commutator of two operators A and B is defined as AB minus BA. The commutator of Pauli matrices sigma I and sigma j, using the work we've already done, the commutator of sigma I with sigma j is 2i epsilon ijk sigma k. So we don't have to write out 6 commutators. That one formula tells us how to do the 6 commutators. We just have to remember how to do the epsilon. Well, that's quite a lot of properties of the Pauli matrices, and I'll tell you that they're actually all interesting and useful properties. We haven't really used the properties yet. We've only said what the properties are, but they actually are very helpful and interesting properties for two-state systems. And we got all those properties without needing to introduce spin 1/2 yet. If you look at a book is going to start teaching you spin 1/2, and it's going to give you the Pauli matrices and tell you what they mean for spin and show you, how they get multiplied and how they get commutated. And you are for sure going to end up with the belief that these magic properties of these Pauli matrices are because of spin 1/2. But I tell you, they are not. They are properties of two-state systems, and spin 1/2 is only one two-state system. Probably the most important two-state system. But the properties of the Pauli matrices do not come from spin 1/2. The properties of the Pauli matrices help us understand spin 1/2. We will use these properties of the Pauli matrices in the next lecture, D3, on spin 1/2 particles. This is the end of lecture D2.